Ratko telling us all about optimizing sparse matrix vector multiplication on which platform?
EPAC.
EPAC. Very good.
Okay. Greetings everybody, and thanks for this opportunity to present our work on the optimizing sparse matrix vector multiplication on the EPAC architecture. In the center of our research is the EPAC core, which consists of several units, but we are most interested about the vector processing units, Vitruvius. Basically, Vitruvius is a long vector processing unit that is bound to achieve really amazing stuff in the future. However, we are interested in the sparse matrices. Even now, the sparse matrices are some kind of mystery in the realm of HPC computing. They are just regular matrices, but the majority of elements are zero. So we came up with a different representation, which we try to omit these zeros and produce smaller storage. However, this opens a backdoor for irregular memory access, which we need to account when dealing with operation with these kind of matrices. We have a different format that optimize storage or computation. Our experiments and our results that we obtained here are done on the FPGA SDV platform, the FPGA software development vehicle, which emulates the VPU, EPAC Vitruvius VPU on the FPGA fabric. We gained access to the HES server at the Barcelona Supercomputing Center. Concerning the formats that we use, the most fundamental one is the compressed sparse row, or CCR. Basically, we are heading from row to row and eliminating zero elements. However, we need to retain the information about the column index, the column index or indexes of columns, and of course we have input vector to calculate sparse matrix vector multiplication. And in these few slides, I will just show the approach, some kind of algorithm. How do we implement this on the VPU? Let's say vector length of 8. So first, we use the information about the column indices to as input to the memory gather operation to collect the elements from the input vector. Then we collect them in the vector register, multiply it, and then we are using a masked reduction. However, this is need to be done because some portions of the vector belongs to one row, some portions belong to the other row. And then we are getting, at each iteration, we are getting one element per time. And this is how it's done. Now, the second approach that we wanted to employ is that instead of memory gather operation, we rely on the vector permutation. We want to let's say to see how the vector shuffling inside the Vitruvius works. So we are collecting the input vector in regular fashion and leaving the vector unit to shuffle the elements. Okay, and these are the results. So we were we evaluated on different matrices. First is DVT 512. The second one is S circuit, and the last one is COP 20KA. And as you can see that the speed up is less than 1. Basically, the vector version is slower than the scalar one. We attribute this to the reduction reduction in the matrix, and besides the CCR, we are also using the LPAC. The LPAC is similar as CCR, but it allows to store some zero elements, which enables better computation and better parallelization. Let's say concerning the SMPV, in the SMP, when using L on the SMPV, we are relying on the iterative multiply and add operation, just doing in this fashion. So we are relieving when calculating the SMPV, we don't use reductions. And in a similar manner as CCR, we are also relying on the vector permutation to see how they behave. Okay, and the results are pretty much better after when we do not rely on the reduction. The speedups are much bigger. So for this first matrices, the DVT is the speedup is much greater. It's over 10. Then for, let's say, other matrices, we have a speedup that goes from 3 to 6. And we see here also from the second matrices that the vector permutation gave us better results than the scatter-gather operation. And a similar thing we can see with the last matrix. Before I conclude, I want to acknowledge the help from our colleagues from the University of Zagreb. This is part of the joint collaboration. And of course, the European Processor Initiative project and Barcelona Supercomputing Center for allowing us the access for FPGA SDV. And here we are open to questions.
Thank you so much. Are there any questions? Yes.
Hello, a nice presentation. I have mainly two questions. Mm-hmm. One is, why are you using reductions on the CSR? Because as far as I know, you can also implement a SPMB with vectors with CSR without reductions, using the same multiply accumulate on a single vector. Have you explored this or?
No, I didn't. This was just work in the progress. We will try to also. This is just this approach that I implemented doesn't give us good results, but it also tells us that reduction is something that we need to avoid when doing.
Yeah, and the second question is, have you compared your approach to other people's? Because at least at BSc, I'm aware of a paper about accelerating SPMB.
We are aware about that paper, and we are trying. We are still collecting results and experimenting with the other formats, and we'll see. We'll try to compare it in the future. The goal is here not to, let's say, find the optimal matrices, but just to explore this trade-off, this two options between the memory gather operation and vector permutation.
Okay. Thank you.
Thank you. Thank you so much.